was saying, there's a website that has nice software for doing Feynman diagrams in LaTeX, and what is your name again? I'm terrible with names. Say it again. Saha. Saho.
Sean Powell.
Saho. All right. Anyway, that's the website, and it's quite good, but I can't quite get it to do what I want it to do. Anyway, we were talking about electron-positron scattering, and what I said was there is a direct amplitude, and we went through the Feynman rules. How far did we get last time? Shall I redo them? Yeah, I think maybe so. Okay, so there's a direct term which I labeled A sub A. I should have labeled it A sub D or A sub S. S is S for S channel, and it's named after the first of the three Mandelstam variables. And if we implement the Feynman rules, what we get is d forth q. We have two vertices, one here and one there. And so they give 2 pi to the fourth E gamma A beta alpha delta fourth of P plus K minus Q. And the other vertex is again the same thing, 2 pi to the fourth E gamma B gamma delta fourth of minus P prime minus K prime plus Q. And I'm going to, I need to redo the LaTeX a little. Let's see, P plus, what, I changed the notation halfway through, and let me go back to.
Hey Kevin, can I just ask?
So it's, okay, I put the K's on the muons.
Kevin, can I ask you a
well,
question
here,
real quick?
yeah, what?
So which set of notes in this and what page are we on?
The best thing is sw.pdf, just SW without anything else.
Okay, which I'm on that one, which page?
And I'm on page 84. Well, 83, or even 82. And I'm going to switch. First, I'm doing electron-positron scattering, but after doing the Feynman diagrams, I'm going to switch to electron-muon scattering, which is simpler because it only has the S channel term. But let's begin with the with electron-positron scattering. But in order to keep the notation the same, okay, all right, so now I've got it straight. So if we have the incoming ones like that, then what we have is, I'm talking about the final ones in this way, so we have here P and P prime, and here K and K prime. So that's the. Well, now that I think about it, this calculation I first did in one notation, and then I switched to the other notation. Anyway, putting in the Feynman rules, what we get is. This is a very bad time. I'm in the middle of a lecture. So here we have U gamma, and you know, I think if I'm going to follow my notes, I'm going to have to follow my notes. Otherwise, there are so many variables that I'm just going to get everything screwed up. So let's just do P plus K and P prime plus K prime. So this is P and K in the initial state, P prime and K prime in the final state. So P's labeling the electrons, K labeling the positrons. So then, applying the Feynman rules, you get U bar gamma of P prime, S prime, that's this one here, and this vertex has a gamma on it. We have 2 pi to the 3 halves, and in fact, we're going to have altogether 4 of these. So I'm just going to write the 2 pi to the 3 half factors as just 4 of them like that. Then this line going out gives us V delta K prime T prime. Then this vertex coming in, we've got U alpha of P and S and V bar beta of K and T. And then we have the propagator, which intellectually is the most complicated part, but to write down is the simplest part, minus I over 2 pi to the 4, A to AB over Q squared minus I epsilon, and as I said, the I epsilon is really not important for tree level diagrams. Let's see, I think okay. So the gammas are associated with the vertices, and this is vertex A, this is vertex B, so we have here beta alpha, and here we have gamma delta, and so this is a consistent implementation of the Feynman rules for the direct process. And if we boil that down just a little bit, it is well, we might as well deal with the 2 pi's maybe right away. The 2 pi's are you've got 2 pi to the 8th up top, 2 pi to the 10th in the denominator. So always we're going to have 2 pi squared for this process. We're always going to have an E squared. When we integrate over d4th q, the first delta function tells us to set q equal to p plus k. So we're going to have p plus k squared. There's a minus I, and there's an A to AB. And then, apart from that, what we've got is, for example, U bar gamma, gamma B delta, gamma delta, V delta, and we can rewrite that as U bar of P prime and S prime, gamma B, V of K prime and T prime. And that, in a sense, describes this final vertex more transparently. And then we have gamma A, beta, alpha, and we have here a beta and an alpha, and so this is V bar of K and T, gamma A, U of P and S. And I think that is the whole story, apart from the fact that we have to substitute for Q, P plus K here, and so we have the energy momentum conserving delta function, P plus K minus P prime minus K prime. Now let's see, is there anything I left out? No, I think that is it. So that's the Feynman rules for the direct process. Now, the exchange process, well, we can say, well, what is the exchange process? The exchange process is if the electrons go along and just exchange a photon, and the positron comes in and goes out, and so you have E minus E plus goes to E plus E minus with a photon going across. If this is P and this is P prime, then this is P minus P prime. And now we can basically just write the Feynman diagram down. It's going to be, but notice we're dealing with fermions here, so we have to worry about minus signs. And so I'm going to do this whole calculation in a little more detail to exhibit the minus sign. So at this point, I'm going to say that AT is plus or minus I E squared over 2 pi squared. It's going to be eta AB over P minus P prime squared for that. And then the vertices are going to be this, the final vertex will be U bar of P prime S prime, say gamma B. Oh no, that's, if this is the second vertex, this should actually be, all right, let me write it down. It will be, okay, let me write the first vertex down. This will be U bar of P prime S prime, gamma A, U of P and S. So in a sense, this one is simpler. There's a U and a U bar, and now we've got V and V bar, and that would be V bar, and this would be KT, gamma B, V of K prime T prime, and okay, all right, so that, oh, except that this eta AB, all right, we've got the eta AB in there, and the eta AB, of course, is going to make this much simpler. Eta AB with a gamma upper A, gamma upper B, we can just replace this by a 1 and just lower this B and make it a gamma A. Or equivalent, we can lower it and make it a B and make this guy a gamma B. And then over here, the eta AB can have the same effect, but let me just write it this way. So these are the two terms, finally, that we have to deal with. Now the question is, what is going on? Well, the initial state is PS, P prime, S prime. No, I'm sorry, it's PS and KT. And this is a dagger of P and S. B dagger of K and T on the vacuum, and the final state is P prime, S prime, K prime, T prime, which is obviously it's the same thing, just a lot of primes. Okay, and of course, since it's final state, we look at it as a bra rather than a cat.
I've got a question.
Yeah.
On that last equation on the first board, so you had eta AB, you had gamma A, and you had gamma B. So if you contract over B, shouldn't you still be left with 1A?
You can contract over either one.
What is it? Oh, you got a lower B on the right side. Okay.
Good catch. Okay, so now let's try to get the look at the direct diagram. The direct diagram starts with a time-ordered product, psi bar x, gamma a, psi x, a of x, psi bar y, gamma b, psi y, ab of y. Okay, so that's the time-ordered product that we're integrating over all of space-time twice. And we have the initial and final states on the right. And so the terms here that we're interested in, if we're doing the direct diagram, is we want to take the parts, the absorbing parts, out to the right. And we'll choose to have the space-time vertex that does the absorption to be y. And so this is effectively, and I'll put a tilde on this because I'm leaving out all the terms that don't contribute to this process. And let me do the easy part. Well, I'll better write down the whole part. So this is psi bar at x minus gamma a psi bar at x, and then I'm going to have t a of x, a b of y, and then here on the right I'm going to have psi bar plus of y, gamma b, psi plus of y. So let's remember that psi looks like this: psi plus plus psi minus. Psi plus has annihilation operators and creation operators for the positrons. Psi bar, by the way, so remember that psi bar is psi dagger beta, which is the same thing as psi dagger I gamma 0. So that's the notation. And this one will have psi bar plus and psi bar minus. And this is just the adjoint of that, basically. So this has creation operators for electrons and annihilation operators for positrons. And I just rewrote this the wrong way, so let me fix this. So the annihilation part here has a B, and this has an A dagger. So this part here is annihilating an incoming electron, and this part, psi bar plus, this is annihilating an incoming positron. And then over here, this is psi minus, this is creating an outgoing electron, and this is psi bar minus, wait a minute, do I have that right? Psi, that should have been psi minus, I think. Yeah, this should be psi minus. Ah, it is, there is a psi minus, and psi minus is creating, whoops, it's creating the outgoing positron, and then psi bar minus is creating the outgoing electron. Okay, so that's all straight. So now you see on the left-hand side we've got the operators that create the final state, and this annihilates the initial state. And we have it in order. We have B, A, and then we take out the A, take out the B, we're back to vacuum. And then over here, when you take the adjoint of this, we're going to have vacuum BA, and then we have A dagger, B dagger, so the A's cancel, the B daggers cancel, everything is in order, there's no minus sign to get back to the vacuum. Okay, so that's what we have. In other words, this thing here is something like a dagger of P prime, S prime, gamma A, B dagger, K prime, T prime, time-ordered product, AA of X, AB of Y, and then B of K and S, gamma B, A of P and S, K and T, this is. Okay, typo there. All right, so that's the direct diagram, or the S-channel diagram. This is called, as I said, the S-channel, and the reason is that P plus K squared is what Mandelstam called S. Now, this channel here is the T channel, and it's named after T, which is the Mandelstam variable, it's the name Mandelstam gave to P minus P prime squared. And I should say that we're using Weinberg's convention, which has 3 plus signs with a minus sign. I think Mandelstam was using the opposite convention. So his Mandelstam variables had S positive, whereas this presumably has S negative. Okay. Now let's do the exchange diagram, and this is an important lesson. So what we have again, once again, is time-ordered product of psi bar, gamma A psi, AA, all this at X, psi bar, gamma B psi, AB, all of that at Y. And so this is, what we want to do now is we want the vertex X to be one that absorbs an electron and creates an electron, and vertex Y is going, vertex Y is going to absorb an electron and create an electron, and vertex X is going to absorb a positron and create a positron. And the way we arrange that is to have psi bar X, psi bar plus X, gamma A, psi minus X, time-ordered product of AAX, ABY, and then over here, psi bar minus Y, gamma B, psi plus Y. Okay, now why does this work? That's because psi plus gives us an annihilation operator for an electron. Psi bar minus gives us a creation operator for an electron. And then over here, psi minus X gives us a creation operator for a positron, and psi bar plus gives us an annihilation operator for a positron. And so you see that's the structure that we've got. And now, however, in order to get it into the form AB, B dagger, A dagger, which is the form we need to match the initial and final states, what we have to do is we have to take this A dagger and we move it across until it becomes A dagger, B, gamma A, B dagger, gamma B, A. But there we've gotten 2 minus signs, so that doesn't cut any ice. But then when we move the B across, we only cross one creation, one fermion operator there, And so this is minus A dagger, B dagger, gamma A, B, gamma B, A. So to get it into the form that we want, namely A, B, B dagger, A dagger, we encounter one minus sign. And so the things that we add together are that AT then is going to have a plus sign. It's going to look like that. And we have to add, we have to say that A is AS plus AT, like that. And so if we put those together, we get as the total amplitude AS plus AT, we would get, and let me skip a little, a couple of steps here. This is energy momentum conservation. And then putting the terms together, we get V bar gamma A, U bar prime, gamma A, B prime, P plus K squared minus U bar prime, gamma A, U, V bar, gamma A, V prime, and let's be a little more careful. This should be a different index. And this is then P minus P prime squared. Okay, so that's what it looks like.
Assuming this is AS plus AT.
That's, oh, thank you. Let me give you a candy. Whoa! Okay, so that is the amplitude. Now, the route from here to the cross-section is, if you do it for the first time, it's a kind of long road. It's intellectually, it's trivial, but the number of manipulations is surprisingly large. And the first step in understanding those manipulations is the derivation of some trace identities. The trace identities are pretty simple, and so let me do some of them. First of all, the trace of gamma A. Remember that gamma 5 can be regarded as a, or to put things differently, if we were in four space and one time dimension, so we were in 5-dimensional space-time, we could still use the gamma matrices, but we would add one that we should call gamma 4, but instead we call it gamma 5 because sometimes people use gamma 4 for gamma 0. Consequently, gamma 5 squared is 1, and it anti-commutes. So what we can say is that gamma A, gamma B is 2, A to AB, where this is the thing for 5 dimensions. In other words, this is equal to minus 1, 1, 1, 1, 1. So those are the relations for the five gamma matrices for 5-dimensional space. Gamma 0, gamma 1, gamma 2, gamma 3, gamma 4, but we call gamma 4 gamma 5 for historical reasons. Here we're pretending to be astronomers. Yes, Sam.
Are these like the same thing as Majoranas?
Are these what?
Like Majorana fermions? Because Majoranas have the same commutation relations.
Well, these are gamma matrices now.
Yeah, but they have the same. I know they're matrices, but I mean they have the same commutation relation, anti-commutation relations
Well,
like Majoranas.
You know, the term Majorana is, you know, like many of these things with regard to names, the name sort of floats around and gets attached to different nouns. And
Yeah, but no, but okay, so if you take a linear combination of creation and annihilation operators for fermions, so it's like A dagger plus A, and...
first of all, the word Majorana is only associated with fermions.
Okay, great, okay, yeah, but
Yeah,
then you have the
so
same anti-combination.
that's what I
you
think
take
you
those,
have in
and then you
mind.
take a different kind of linear combination, but you get those same commutation relations, so I was wondering if they're like the same thing.
Well, Majorana fields anti-commute with themselves.
Okay.
But, and so do Dirac fields, all fermion fields do. They always satisfy anti-commutation relations, and we say that casually, but you know, there's a deeper understanding there that I don't understand, and I don't know if anybody does. I suppose Ed Witten does, but he hasn't told me what it was.
Have you met Ed Witten?
Huh?
Have you met him?
Oh, yes, I know him. I wouldn't say well, but I've known him for 40 years or so. Anyway, he's a nice man. So let us put gamma 5 squared here. So we haven't made any change because gamma 5 squared is 1. But now gamma 5 and gamma A anti-commute, so this is gamma 5, gamma A, gamma 5, with a minus sign. But the trace is cyclic, so this is also minus trace gamma 5 squared, gamma A, and gamma 5 squared is still 1, so this is minus trace of gamma A. So the net result is the trace of a single gamma matrix is 0. And that's kind of obvious from the form of the gamma matrices. The gamma matrices are basically 0, sigma something, sigma prime something, 0. So obviously the trace is 0. The trace of two gammas, well, we use this relation which tells us that gamma A, gamma B is equal to minus gamma B, gamma A plus 2 eta AB. And so we can write that as trace of 2 eta AB minus gamma B, gamma A. But the trace is cyclic, so this is minus 2 trace gamma A, gamma B plus 2 times the trace of eta AB. That's 2 eta AB, but the trace of 1, see, there's a 4x4 identity matrix lurking here. The trace of that is 4. So what we get then is 2 trace gamma A, gamma B is 8 eta AB, and so trace of gamma A, gamma B is 4 eta AB. Okay, so that's one of the trace identities. Another trace identity is the trace of an odd number of gamma matrices is 0. And for that, we just imitate this. So let's see if I can do it here. Trace, and I'm going to write it as gamma O. Gamma O is the product of an odd number of gamma matrices. Any odd number, 3, 9, 11. We can write that as trace gamma 5 squared gamma O. But now if we move the one gamma 5 through an odd number of gamma matrices, we're going to get an odd number of minus signs. Oh, this gamma O doesn't have any gamma 5s in it. It's an odd number of ordinary gamma matrices. So this is minus trace gamma 5, gamma odd, gamma 5. So this, maybe I should write this as odd rather than as O, because gamma O looks like gamma 0. So that's a minus sign. Then the thing is cyclic, so we can move the gamma 5 forward, so that's trace of gamma 5 squared gamma odd. And that's 1. And so altogether this is minus trace of gamma odd. So now we've got the trace of gamma odd is equal to minus the trace of gamma odd. That means trace of gamma odd is 0. Yes?
So gamma of the odd means
A product of an odd number. In other words, it's gamma A1, gamma A2, gamma A2n plus 1. But none of them is gamma, no gamma 5s, only ordinary gammas, 0 to 3. Okay, so we've got that. Now, to use to find the trace of 4 gammas, which is really important, we're going to use this relationship several times, namely the fundamental anti-commutation relation for gammas.
So we start out with trace of gamma A, gamma B, gamma C, gamma D.
And once again, I'm only talking about ordinary gammas in 4-dimensional space, gamma 0, gamma 1, gamma 2, gamma 3. All right, so the first thing we do is we're going to start moving gamma A to the right. So we get a term when we cross here, we get a term when we cross there, a term when we cross there. So this is, first of all, trace of 2 A to AB minus gamma B, gamma A, gamma C, gamma D. And we can say that that's then the same thing as trace of 2 A to AB, gamma C, gamma D, minus gamma B, gamma A, gamma C, gamma D. So we're going to keep this term, 2A to AB, gamma C, gamma D. And then we're going to write that as minus gamma B, 2A to AC minus gamma C, gamma A, gamma D. And so this gives us trace 2A to AB, gamma C, gamma D, minus 2A to AC, gamma B, gamma D, plus gamma B, gamma C, gamma A, gamma D. Now we move the gamma A to the right one more time. We get trace 2A to AB, gamma C, gamma D, minus 2A to AC, gamma B, gamma D, plus 2 gamma B, gamma C, A to AD, minus gamma B, gamma C, gamma D, gamma A. But now, that last term is the same as the first, apart from a minus sign, because the simplicity of the trace. In other words, by simplicity of the trace, what we have is that the trace of ABC is equal to the trace of CAB. And so we can move the gamma A to the beginning without changing anything, so we're going to have 2 of these equals that. And so finally the rule is trace of gamma A, gamma B, gamma C, gamma D equals, and what we have left are traces of etas times gammas. And so this is then a trace of A to AB, gamma C, gamma D, minus A to AC, gamma B, gamma D, plus eta AD, gamma B, gamma C, but the trace of two gammas is, where is it? Trace of two gammas is 4 times an eta. And so this is going to give us, this is then 4 times eta AB, eta CD, minus eta AC, eta BD, plus eta AD, eta BC. So that's this formula for the trace of the product of 4 gamma matrices. There's one more rule that I'm not going to try to prove, but I'll just tell you what it is. Trace of gamma A, gamma B, dot, 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 gamma Y, gamma Z is the same thing as trace gamma Z, gamma Y, dot, 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 gamma B, gamma A. In other words, you can reverse all the gamma matrices and nothing changes. Okay, now I want to do in more detail the cross-section for electron-positron. The process electron plus positron goes to mu plus plus mu minus. So muon plus anti-muon. So the process is E plus plus E minus goes to E plus plus E minus. The reason why I want to do this is that it's hard enough to do the to do all the steps. If we were going to do E plus E minus in the final state, we would have to have the exchange diagram. So then we would have the sum of two Feynman diagrams. We have to take the absolute value squared of that and then go through a large number of manipulations. And the complexity is something that Weinberg goes through for Coulomb scattering, because Coulomb scattering also, not Coulomb, Compton scattering has two diagrams that you have to add together. Do you have a question?
Yeah, I was going to ask about the muon. Like, where is it as far as, I don't know, like I see electrons in our original QED Lagrangian. I see photons, but
okay,
what
great
are
question.
muons and where
Well,
are
there's a famous quote attributed, I don't know if it's an actual quote, but it's attributed to a physicist at Columbia, whose name I forget. Anyway, he was there during the Second World War, working on molecular beams and things related to the Manhattan Project. In fact, the reason the thing is called the Manhattan Project is it started in Manhattan. Some of the early work on nuclear weapons was, you had to compute the you had to measure the, I say compute, what a joke. You have to measure the cross-section or the rate of fission of the cross-section for neutron plus U-235 to go to fission suitable fission products and other and you have to know what that is as a function of energy and so forth. The same thing for U-238 and so forth, and plutonium for that matter. Some of that work started at Columbia. Anyway, this guy, when the muon was discovered, he said, who ordered that? And the reason was that as far as we know, the muon is the same as the electron, it just is heavier. And so in the standard model of particle physics, what you've got is you have an up quark, a down quark, an electron neutrino, and an electron, and then you have a charm quark, a strange quark, a muon neutrino, a muon, a top quark, a bottom quark, a Tor neutrino, and a Tor lepton. And these three guys here have exactly the same interactions, but just different masses. When I say exactly the same interactions, I mean as far as we know. And so each of these is called a family or a generation. And so to put the muon in, let's see, if I write down, I can write down the Lagrangian for, if I can find the one for electrons, and I'm having trouble doing that. Yes, there it is. Okay, so, well, after a while there's so many equations you can't find anything. Yeah, there we go. So, the action density, in other words, looks like this: minus a quarter FAB, FAB, minus psi bar for electrons, gamma A, dA plus IE, AA, plus ME, psi E. And then we just write down another term which looks exactly the same. The charge is the same. And the difference is that the muon is about 200 times heavier than the electron. The muon weighs around 105 MeV. The electron is around half an MeV. And so that's the way it looks. So doing the calculation with muons, we just treat the muons the same as electrons.
Why is the mass not squared? Should the mass be squared?
Say it again?
Is the mass usually squared, or is the mass usually not squared?
Ah, great question. In bosons, it's put in squared. In electrons, it's put in linearly.
Okay.
And the reason is that in the electron Lagrangian kind of, in other words, the equation of motion for the Dirac field is really 4 equations. And you can combine those 4, you can reduce those 4, you can take the 4 equations and rewrite them as 2 equations that are second order. And when you do that, you get the mass squared. I'll give you candy when I get to that side of the room again. Okay. So now, luckily, we only have a direct term. And so the amplitude is a sub s, and it's exactly the same as the previous thing. Maybe I should write down the diagram first. The diagram is E minus in, positron in, photon, mu minus out, mu plus out. And so, and now I'm going to use a different notation. Let me get it straight here. Right, now it's going to be, this is going to be P, and this is going to be P prime, and this is going to be K and K prime. That's the way I've got it written here, but I'm just wondering what happens farther down. Do I switch? No, I'm using, okay, I'm using K, so I'm switching notation here for the momenta. The P's are going to be for electrons, K's for muons. And so we can write this down immediately. It's just the direct term for electron-positron scattering, and P plus P prime minus K minus the incoming, minus the outgoing momentum, and then this is times V bar of P prime, S prime, gamma A, U of P and S, and U bar of K and T, gamma lower A, V of K prime, T prime, and we divide by S, which is P plus P prime squared. Okay, so that's the single amplitude for electron, positron goes to mu plus mu minus. So this part is easy, and it's the part that's intellectually subtle and interesting, but because of Feynman's rules, you can write it down and in no time at all once you become familiar with his rules and understand them and so forth. So this part is very easy, and the step from here to the cross-section, as I said, it's a zillion intellectually simple but computationally difficult small steps. On the other hand, we have computers today, and so people who do this for a living, I don't think do it with their fingers. They have their own favorite programs, and they just enter the right variables, and bingo, all the traces and gamma algebra is done for them, and so on and so forth. So but if you write down the Feynman diagram, you can nonetheless realize that a lot of things fall out, and it's worth knowing what's going on. I mean, in other words, the P plus P prime term is important, and what is it? Well, suppose we were, suppose we compute this in what is both the simplest and the most experimentally sensible Lorentz frame, and that is the center of momentum frame, and that's the frame of the Earth for colliding beam experiments like the collider that used to exist in Fermilab and the one that still exists, the Large Hadron Collider, and what used to be at SLAC, which was an E plus E minus machine. So there, P plus P prime, the momenta are equal and opposite because you have a colliding beam experiment. So when you add them together, you just have P0 plus P0 prime, and we're squaring this, and so you have minus, let me get this straight. You have, minus P0 plus P0 prime squared. So the sum of the zero components is P0 plus P0 prime squared. Is then a minus sign. But on the other hand, since they're obviously, if you do the experiment, you normally have the same energy in both beams. And so this is 2P0. So this is minus 2P0 squared, and so this is minus 4P0 squared, which is energy. So this is minus 4E squared, where this is the energy in the beam. And so the amplitude goes as 1 over E squared. The cross-section goes as 1 over E to the 4th. Now, when I say the cross-section, I just mean the cross-section that's related to absolute value of AS squared goes as 1 over E to the 4th then, apart from the things that occur from the traces. So in other words, traces squared over e to the fourth. Now suppose instead that we were considering not this process, but the process where you would have a Z0 going across here. So in other words, here is the Lagrangian. This is for the U1 theory, the abelian theory. But if we were doing the non-abelian theory, we would have a matrix here with 3 gauge fields, the photon, the Z0, and the W's. And we wouldn't have just electrons, we'd have neutrinos, and we'd have muons and mu neutrinos. Then we might have a process, one of the processes would be a Z0 going across. And then it would be 1 over p plus p prime squared, and it's always it's been so long since I've written down a propagator for a non-massive field, so it would be plus mz squared. So there we would have 1 over mz squared minus 4e squared. And so you see you have a pole there when the energy is half the energy of the z. And so the cross-section has a huge peak. And in fact, that, of course, was seen at the large, what was called LEP. The Europeans have a much more sensible way of naming things. They call it the Large Electron-Positron Collider and the Large Hadron Collider, whereas we, the American physicists, called it the Superconducting Super Collider, and the congressman thought it was super expensive and canceled it, which is really too bad because it was a much better machine than the Large Hadron Collider.
Couldn't they have said it was largely expensive?
What?
For them? Couldn't they just said they could have just said it was largely expensive if they were trying to?
Well, they should have called it the Large Hadron Collider, yeah.
Yeah, and then that congressman would have said, well, it's largely expensive.
Well, yeah, but superconducting super is really super stupid.
I think it sounds cool.
Huh?
Well, I think it sounds cool.
I think the big thing.
Well, that's the trouble. They thought it sounded cool, and to 13-year-old boys it sounds cool. But
Yeah, 13-year-old boys are the future. Well, Anglo, 13-year-old boys Anglo.
might be the future, but the House of Representatives is not is composed by 50 and 60-year-old men, not 13-year-old boys.
Yeah, everyone has a kid inside themselves.
I think the big issue with it though was that it was the cost overruns, because all of these government contracts, everybody underbids. It goes to the cheapest person, and then 10 years later, it's 400% over cost, and they're only 40% finished. So
Yeah, and if you're Lockheed Martin, you can get away with it. If you're a bunch of physicists, you can't. But they weren't 400% over.
they were way, way over. I was reading about it. I'm older than these guys. I was reading about it.
Here, I owe you a candy.
And,
Oh, thanks.
so Leon Letterman was writing about it a lot. So,
You know of any physicists that got stranded in Texas? I heard like of a bunch of people that came to Texas, to like universities in Texas to work on the superconducting super collider, and then it was canceled, and so there were just tons of physicists that were like, oh crap, like.
Yeah,
you
yeah. A
do
lot of
stuff, and
people,
now we're
a
just
lot of
working at
people
this
gave up
university.
really marvelous
Yeah.
academic jobs to go to Texas,
Mhm.
and were then left hanging. I knew some of them, and the job market, of course, has been terrible in particle physics, especially theoretical particle physics, for 50 years. It's gotten worse and worse. And so theorists were really screwed. Experimentalists could manage because they could always get job doing something. And all right, well, this is all apart from that. So anyway, that was seen at LET. And so now let's see. This is our amplitude, but of course the actual cross-section is the absolute value squared, so we have to take the absolute value squared of the trace. And now you see why it is that I wanted to have electron-muons. Electron-positron goes to mu plus mu minus. And the reason is that then we simply have to take the absolute value squared of this rather than the absolute value squared of the sum of two terms. And we'll see that this thing is enough of a headache. Although with computers, I said it's you know, a few nanoseconds of computation. So we have to take the absolute value squared of that, and in particular, if we look at the first term, the electron term, this is the muon term then. We look at the first term, what we have is V bar, gamma AU, U bar muon, gamma A, V muon, times the complex conjugate, which is V bar, gamma B, U bar, muon, gamma B, V muon, complex conjugate. In other words, over here, this amplitude is a sum over gamma upper A, gamma lower A, but we multiply it by its complex conjugate, which is another sum over gammas, but of course we have to use a different letter for that, for those gammas. And so the first thing is we have to figure out what do you do with a, when you complex conjugate something like that. And so let us look at just simply V bar gamma AU complex conjugate. Well, this is V dagger beta gamma AU complex conjugate. And of course, you just these are vectors, these are matrices, that's a vector. And so this is U dagger gamma A dagger beta dagger V. But what is beta? Beta is I gamma 0. Beta squared, therefore, is 1, because gamma 0 squared is minus 1, and I squared is minus 1. And moreover, beta is Hermitian. And something that we proved back when we were considering special relativity and so forth, was that beta gamma A dagger beta is equal to minus gamma A. Okay, so that means that we have a very simple expression here. We can just stick in, first of all, this is just beta. So this is U dagger gamma A dagger beta V. Now beta squared is 1, so we can stick in 2 betas. But beta gamma A dagger beta is just gamma A, and so this is equal to U dagger beta gamma A V, and this is U bar gamma A V. So in other words, if we have something V bar gamma AU, the complex conjugate is just U bar gamma AV, so it's very simple. So this structure that we have to compute isn't so bad. In other words, we have to compute, we have V bar gamma A U, V bar gamma B U. So this is the electron part. So there's also a muon part, but I'm doing the electron part times the complex conjugate of the electron part. And so this is actually V bar gamma A U, U bar gamma B V. So that's what we have to compute. And now you see that these guys have the same momentum and spin index. And this one and that one have the same momentum and spin index. And in most experiments, we don't measure spin. And so we're going to be summing over the initial spins, summing over the final spins. And so what we're going to do here is a sum over S and S prime of this. And that means we can use the spin sum formulas that we derived laboriously a week or two ago, namely a sum over S of U, L of P and S, U bar, and we had just star and a beta, so maybe I should do this in 2 steps. What we had was U star M of P and S equal to minus I P slash plus M beta over 2P0 LM. So that was the formula. But now if we multiply from the right by beta, we get sum on S UL U bar M is equal to minus I P slash plus M beta squared, which is 1, so just LM over 2P0. So that's our spin sum formula, and the other one for V's is sum VL of P and S. V bar M of P and S is minus I P slash minus M LM over 2P0. So the difference between positrons and electrons is a minus sign on the mass term, plus sign, otherwise it's the same. The muon part of the sum is U bar muon gamma A V muon U bar gamma B V complex conjugate. And notice the electron part had an upper index, the muon part has a lower index. And so this is the thing that goes there. And so this is U bar muon gamma A V muon gamma B U bar muon. Okay, so now let me let me use the spin sums to write the electron and muon parts of these amplitudes. And so what we get is that the sum S and S prime B bar gamma A U bar gamma B V, and literally this is sum over S and S prime J L M and N. And so this is then V bar J, P prime S prime, gamma A J L, UL, P and S, U bar M, P and S, gamma B, MN, BN, of P prime and S prime. So that's literally what we've got. And now we use the spin sum formulas to write that as, first of all, 1 over 2p0 sum S prime JL Mn V bar J P prime S prime gamma A J L, but now this part is minus I P slash plus M L M gamma V M N V N of P prime S prime. And now you see you can rewrite that as 1 over 2p0 S prime JL Mn Vn of P prime and S prime V bar J of P prime S prime gamma A JL minus I P slash plus M LM gamma B Mn. This then becomes another spin sum, and so this is 1 over 2p0, 2p prime 0, sum, and there's no S here, so there's a typo there, JLMN, and this is then minus I P prime slash plus M, no, minus M. Right, minus M, because it's these are the positron terms. Minus M, NJ, gamma A, JL, so it's NJ, JL, minus I, P slash plus M, LM, gamma B, MN. Okay, now you notice this is just a trace. Sam, look, trace.
Okay.
You see, NJ, JL, LM, MN, summed over everything is a trace. So this is 1 over 2p0, 2p prime 0, trace of minus I, P prime slash minus M, gamma A, minus I, P slash plus M, gamma B. So it's a trace of something that's quartic in gamma matrices. The muon term, so this is the electron term. The muon term is U bar gamma AV, U bar gamma BV, star, and if you sum over everything, you have sum over U bar gamma AV, V bar gamma, I see I've got a, I've got my A's and B's a little bit confused here. Anyway, this turns out to be 1 over 2p0, 2p prime 0. Actually, these are muons, so these are k's. 2k0, k prime 0, and it's the trace of minus I, k prime slash minus m muon, gamma b, minus I, k slash plus m muon, gamma a. So notice up here we had upper indices, gamma A, gamma B. Down here we have lower indices, gamma B, gamma A. And I'm not sure about whether this is A or B. I just noticed there may be a typo here. But we're basically out of time here. So, so you can see we can now use our formula for the trace of 4 gamma matrices and the trace of 2 gamma matrices to evaluate these two things. That turns things into Lorentz invariant forms like P dot P prime, P prime dot K, P dot K, K dot K prime, and so forth. And also, there are terms that are tiny and terms that are of normal size. These terms, ME times ME, is very small because this is half an MeV, this is 200 100 MeVs. It's a factor of 200. And so what I think we'll do is we'll set the electron mass equal to 0 in the rest of the calculation, which is what people normally do. All right, is there a further question? All right, why don't we turn the thing off then?